Like the names. Come on in, everyone. Just wait for more people to come, so we'll be done or be ready to start pretty soon. Anybody have any questions while we're waiting for everybody else? All right, got more people coming in. Only got 4 of you. That's a little short. I really don't want to start this early without any more people than this. I got 2 more. That's looking better. 4 more now. We are jamming. We are jamming. We are jamming. Yeah. Going back to my Rastafarian roots. uh, Okay, I think that's enough for me to go ahead and get started. It's a whole minute late, so we probably should start anyways. Anybody have any questions before we get started? I'm going to try to ask that of you at the beginning of every class, but sometimes I get kind of excited about what I'm covering and I'll just jump right in. So if I ever forget and just jump right in like that, and you guys have a question, this opening part of class is when we should be asking questions about any homework problems you've had or something like that. If it starts to take too long, using up too much of a class, then I'll save the rest for the end. But in general, we normally start it that way. I'm also going to basically make the end of all my Zoom meetings open for all my other classes and all my other students for Zoom hours, like office hours. So like by our 6:40 tonight, when this is over, someone from another class could actually log in around 6:40 and start asking me questions. So that's something that's going to be open to you guys as well. I want to tell you that we are in chapter 1. Again, I'll wait for questions if you want to type them in the chat or whatever, or if you just speak up. But since I didn't have any immediately, I'm going to go ahead and recap what we did. I did talk about how science works and models and theories and laws, measurement and uncertainty and significant figures we talked about. I've even put the documents that I told you I would be giving you. I've put those in week 1 module. Scientific notation, your book does cover. Y'all should know that already. So I usually don't cover that at all in this course, but if someone needs it, make sure you ask me. I will make up a special Zoom video or I'll meet you one-on-one. When I get back into school, I can do that at school, or I can meet you one-on-one online with a Zoom meeting as well. But we did basically sort of touch on that percent uncertainty versus significant figures. Again, that in the video I offered you, reading this in the video I offered you in week 1 should help you. Approximations. I'll just tell you that there's a type of calculation we call the Fermi calculation or a Fermi calculation named after Enrico Fermi. And Enrico Fermi was a Nobel Prize winning physicist. Well, I needed it for anything other than homework this week. So someone just asked me if they needed their book for anything other than homework this week. No, and if you don't have your book, did you already try accessing the online homework system? Have you been there yet, Caroline?
I saw the free trial. I just wasn't sure if we would need the book this week.
No, I'm wondering if the free trial came with the ebook too. That's why I was asking you. So if you find that, let me know. I am curious because it used to always include it, and I was told that they're not selling any kind of license without it anymore. So if you get access, you get access to the ebook either way. So
Okay,
you
I'll check.
okay. Uh,
So,
go ahead. Someone else?
Uh, I'm currently on the free trial and it does have Pearson e-tags.
It does? Okay, cool.
Just
Thanks
like
for that, Kim.
throwing out there.
Awesome. So what I was saying was there's a section 1-3-5 on approximations that not quite the section that I'm thinking of, but like I said, I would just want to point out that there's these calculations called Fermi calculations. And in fact, there's a biography of Enrico Fermi called The Last Man Who Knew Everything. He was that kind of guy. He was, probably someone that would have been brilliant on, let's say, Jeopardy or something like that. Uh, and he likes to quiz people about facts of nature, and he kept a buttload of data and information in his head. I've tried to do a lot of those things. I have a lot of constants stuck in my head. I've got several poems I've memorized and various things like that. So that's always a good skill to hold on to and to try to build, because it helps you, evidently neurologically it helps you as well, but it just helps you be a little more confident, a little more uh, interesting at conversations. Let's put it that way. So he would, for instance, had one person ask him how many piano tuners he thought there were in San Diego, and he like within a couple seconds gave him an answer. And if you were to take the time to look up the actual right answer, in other words, to go and find all the piano tuners in San Diego in that 1950s era, you would have found that he was within a factor of within a factor of 10. And that's what we mean by approximations and estimates and things of that sort, is just be able to oh, thanks, here's a free Google Drive download for the textbook someone posted. That's great. Anytime you can find that, that's an excellent thing to share. I have no idea whether it's illegal, so we're just gonna go over that and be done. And it might be an older edition, in which case there's no problems, but you'll get plenty of information out of it. But thanks for that. uh, so his calculations would be stuff like that, which you probably don't know, but at that time he would have known the population of the city and all that good stuff. Just like now, it's not unreasonable for me to expect that you guys know the United States has a population of about 370 million. The Earth is on the order of 7.5 billion people right now. We also, practice things like what's the circumference of the Earth, or roughly how wide's the United States, little things like that that we sort of keep in our head. Some of that data is really important. And then when you get into your specific field, you're going to find that certain numbers are very important to you, and those will be memorized. But that's sort of what we're going for. But to give you an idea of a Fermi type calculation, for instance, I can ask you how many fruit flies will fit in your room. Okay. Ideally, this would be a scenario I'd ask you like in a room. I'm in the room with you, and that would be much better. That way, we can all agree roughly how big the room is. I'm not in any of your particular locations right now, so I don't know how big the room is. It'd be hard for me to estimate, to see if your estimate was good. But seriously, think about that. How many fruit flies fit in a room the size that you're in? That's a good question. Some of the ones you'll see in your online tests and practice tests are things like a person lives to be 80 years old. About how many times did his heart beat? Okay, that's another type of question. I've also seen things like on TikTok and Instagram where people are making millions of dollars for no good reason, but in some sense they're entertaining us. So you see these people, they've got Ferraris and cool stuff like that. They live in nice houses and they're doing stupid stuff like I watched one guy fill up a shower stall with cereal, like Fruit Loops or something. And I was a little disappointed because he repeatedly had to go to the store because he kept running out of Fruit Loops. And I'm like, if you'd had a course in physics, you probably could have get a good estimate and not had to go 2 or 3 times. So that's something you should be able to do. Can you estimate how many Fruit Loops it'd take to fill up your shower? Uh, and that's some basic geometry. You can take a poke at roughly what the size, diameter of and thickness of a Fruit Loop is, and then you can estimate the size of your shower, uh, turn basically the volume all the way up to the wall and the top of the door, and then you divide the volume of that wall by the volume of a single Fruit Loop. Maybe you have some Fruit Loops. You could actually weigh the Fruit Loops so you know how much they weigh, and then you could get an estimate of how many are in a box, and then you could use that idea to actually determine how many Fruit Loops it take in terms of boxes. And you probably wouldn't, you definitely wouldn't be off by more than by 10 boxes. Let's put it that way. Okay, so that's some of the stuff you should be able to do. I can't think of any more right now. Another one. One of my physics instructors asked us one time on a test is what's the wavelength of the waves that bats use to determine their location? And that seems like a really open-ended question. But luckily, I happened to know at the time because I'd been looking at these weird bats outside of my house by the light at night, and I noticed they were eating mosquitoes. So I was like, okay, well, in order for them to bounce or echolocate a mosquito, the wave has to bounce off the mosquito and come back to them. And if that's the case, that means the wavelength of the wave has to be comparable to the size of a mosquito. So once I estimated the size of a mosquito, I then knew the wavelength of the wave that they use for echolocation, and I actually got the right answer. So those are neat little things that hinge on physics facts and also some random data. The cool thing is you guys nowadays have the internet. We used to not have that. We'd actually have to look up in books to find stuff like the population of the US and the population of the world. So you can find a lot of information at hand. So by all means, give that a try. That's really cool. In fact, if you really want to look for a cool book to learn about doing that thing, a guy over at ODU, dang it, his name just escaped me. Larry Weinstein. That's it. He wrote Guesstimation, and then he wrote a second edition called Guesstimation 2.0, and he does all sorts of stuff like that. Another calculation, by the way, this is kind of interesting. If you happen to see Oppenheimer recently, or once it came out, you know that there was one scene where this particular guy holds up some I want to say it was like dirt or little pieces of leaves or something, and after the Trinity explosion, he drops it and watches what happens. Well, that was Enrico Fermi, and Enrico Fermi just had an idea. Hey, let me drop these things that'll float a little bit in air and use that to estimate the uh, actual kilotonnage of the nuclear weapon. And I know how he does that. You probably don't necessarily yet because you haven't covered that type of material, but that's pretty impressive if you can just drop some leaves and watch them move and get an estimate of exactly the power of the nuclear weapon you just dropped. That's a pretty impressive thing. So that's the kind of stuff that Enrico Fermi did. I definitely recommend you read, books by Feynman, like Surely You Must Be Joking, Mr. Feynman, or The Pleasure of Finding Things Out, or What Do You Care What Others Thinks. Those are three good autobiographies of Richard Feynman, and they tell great stories about not only Feynman but stories about Enrico Fermi and cool stuff like that. All right, so let's get out of that part. Your book does a little paragraph on accuracy versus precision. So I want to tell you one thing is the precision is a measure of how consistently you can get a particular number when you're measuring a certain quantity. So if you're measuring, say, the length of a aluminum block like this or something, uh, if I make 20 measurements and the smallest one is 5.28 centimeters and the largest one is 5.29 centimeters, we would call that very high precision. If I made 20 measurements and the smallest was 5.28 centimeters and the largest was 6.4 centimeters, we would call that really poor precision. But if we took the average of all of those numbers in either case, we could then compare that average to, let's say, a measurement that some super being had made for us. Then we're comparing that number to the correct answer. So when you start comparing a measurement or a number to a definitively correct answer, then you're talking about accuracy as opposed to precision. So one of the hallmarks of precision is the number of decimal places you can put on a measurement. So for instance, the fact that I told you 58.2 centimeters up to 58.3 centimeters or something like that tells you I'm really only measuring to one decimal place, and I had very small range in it. So the uncertainty must have been around plus or minus 0.1 or 0.2 centimeters. What really tells you that is if you make one of those frequency plots that looks like a bell curve, that would be a plot of number versus number. And the numbers would be the data points of all the measurements you made, like the 5.82, 5.83, 5.8. Put all those on there. And then for each of those numbers, how many trials had that measurement? And that's what you plot on the vertical axis. And what you'd get is something that hopefully looks like a bell curve. And the width of that bell curve is really a measure of the precision. Well, it turns out the width of that bell curve in one case is the standard deviation. And then if you do a bell curve of averages, say from several labs, then the width of that bell curve would, or half the width of it in both cases, would be what we call the standard error, which we'll learn about a little later. So just remember, precision really says something about how consistently you can do something, but it also has to do with the number of decimal places you're allowed to use. Okay, the fewer number of decimal places you're allowed to use, the less precision you have. Okay, any questions on that? All right, so your book does a blurb. That's section 1-3-6 on accuracy versus precision. Then it goes into units, standards, and SI system. I had already started on that, so I want to go on. And I'd even told you a little bit about the extra credit problem I told you. So let's get starting from right there. So I'm going to start off by drawing that thing I gave you a mnemonic for, specifically the prefixes for the SI system. Okay. So I'm going to share my screen, which I often forget to do, and we'll just draw away on here until someone says, Mr. Younger, we can't see what you're writing. So I'm doing so pretty good right now, but do be advised, I sometimes uh, go off like that and sort of forget what I'm doing and might mistakenly do something. So please let me know when I do something goofy like that, just to, help your class go a little better. All right, it's going to take a couple seconds for it to get up there, but it's working now. All right, so hopefully you guys have already come up with a really awesome mnemonic yourself, so you don't have to use one of the childish ones I warned you about, which is, by the way, an ongoing problem. But yeah, try to make up a better mnemonic for that and send it to me. I'd love to use it rather than, my childish stuff. So let's start off here. I'm going to say T, we know is for tera, and then it's dot dot. G, we know is for giga, and then it's dot dot, and then capital M, we know is for mega, dot dot. Uh, you might think Megamind the movie. I think he might have been played by, I can't remember who he's played by, but one of the guys was played by Brad Pitt, and I think that might have been him that was played by Brad Pitt. So tera, giga, mega, kilo, hecto, deca, and then a blank for the base unit, and then deci, and then centi, which I told everybody is another. Centi is the traditional one, but if you work in the OBGYN industry, they'll also call that a sonometer. And then after the centimeter is the millimeter, dot dot, micro, dot dot, nano, dot dot, and then pico. So those are your prefixes. And this, of course, is the base. And some bases are, for instance, they're the meter, the gram, the second, the Kelvin, the degree Celsius, the liter. There's also lumen, which I think is LU. There's candela, which is CD. There's amps, which is A or amperage, and there's V for volt. So there's a lot of different things. Notice none of those have prefixes on them. The kilogram technically has a prefix on it, and in some sense, we think of that as the base unit for the SI or MKS system, but that's just the base unit in the sense that if an equation is made for the SI system, you need to use kilograms in there, not grams, but the base is still the gram. Okay. So we got that. Another valuable thing that we see with this, I showed you how you could, in principle, convert units on this. Actually, did I show you how you could convert units on this? Let me double check. Yeah. Oh no, that's the previous. Okay, that was a different day. Let me kill this one. Let me kill this one. Let me kill the. Okay, this is the one I want. So we did the SI Yeah, so I did show you that. Cool. All right, so yeah, I showed you how to do those unit conversions, and I showed you that weird thing, and then I showed you this stuff and gave you a hint on that. And the actual post has been uh the actual post for this extra credit for calculating the minimum surface area that has been posted in week 1. So let me go back to the actual correct doc, which is the one we're using right now, which is this one. I just realized I have a typo on it, but yeah, we're there. Let me fix that real quick. I'll need a capital N right there. Okay. I just had to change the name of the file. All right. So now that we got that, I'm going to show you how we can use this still for units, even though we're not going to use that thing where we put some god awful answer on there and then count the number of moves and which way we're going. So let's start off with unit conversions. So with unit conversions, there's basically a fundamental principle at play here. And the fundamental principle is if you're really converting a unit, then you're not allowed to do anything to the number that was given to you if that thing actually changes the value of the number we gave you. Okay. Uh, so that means you can add 0 to it. That's fine. You could subtract 0 from it. That's fine. You could take the integral and then take the derivative of it, and that would be fine because that would actually be, two opposite actions on it. You could take the derivative and then the integral. So that would be opposite actions in the opposite order. That would be acceptable. Of course, if it's just a number, you can't really do that very well because, you can't take the derivative of a number and get anything other than 0. And then if you integrate 0, you're not necessarily going to get 0. You're going to get a constant. So that one's a little weird. But can anybody think of anything else you can do to a number? Another mathematical operation that will not change it. So I
Divide
said,
it by 1.
there you go. Divide it by 1 or multiply it by 1. Exactly. So that's exactly what the goal is here. It turns out that a large number of units can be converted from one to the other by multiplication. I call them multiplicative units. But things like decibels, if you ever heard of that, decibels, one thing they use that for is to measure the intensity of sound. If you wanted to convert that from decibels to energy delivered to your eardrum, that will not work. I cannot multiply that by 1 to make it work because it turns out that's a decibel means 1/10 of a bell, and a bell is found by taking the logarithm of a ratio. So you can't do that one that way. I can't convert from Kelvin to Celsius multiplicatively. Everybody knows that the conversion between Kelvin and Celsius is you take the Celsius number and subtract 273.15 Kelvin from it, and that gives you Kelvin. You also can't convert from Celsius to Fahrenheit because that's a linear expression, and you can't convert between Fahrenheit and Rankine scale either because that's another additive thing. So those are some units that can't be done this way, but just about everything else really can. Okay. So our idea is to use the value 1 and then to realize that 1 can also be 1 over 1. There's a version of 1. And then you say, well, wait a second. Wouldn't 2 over 2 also be 1? And you're like, yeah. And you say, how about pi over pi? Well, if you put pi over pi, that's 1 as well. So what you're seeing is as long as the numerator and denominator are equal, then that's a value of 1 as well. So let's make it a little more abstract. Let's say, what about if I put 1 foot in the numerator and I put 1 inch in the denominator? Since 1 foot is, oh, excuse me. I don't know why I said 1 inch. Obviously, I had a little bit too much to drink before I came to work today. I'm playing, folks. But I got Caroline's attention, so that's good. Okay, 1 foot is equal to 12 inches. And then 12, here's another one, by the way. 1 foot is equal to 12 inches, allows you to do 1 foot over 12 inches. But guess what? You can also do 12 inches over 1 foot. Okay, so that's our trick. What we have to find is an equality statement. We need to find an equality statement from at least the unit you have to some other unit. And then hopefully you'll find a equivalent statement for the unit that you converted to another unit that might be in some sense closer to the unit you want, and maybe to another one, and maybe to another one, and keep on until finally you get ultimately to the final unit you want. So now I'm going to demonstrate that straight out. So let's assume we have 1.0 times 10 to the negative 6 tera grams, and I would like to convert this to, let's say, nanograms. So this is our example. Now, remember how we would have done this yesterday or the last meeting? I would have drawn an arrow right on under the capital T, and then I would have taken and gone from that arrow and draw a jump from that arrow to the first dot, second dot, G, dot, dot, M, dot, dot, K, dot, or excuse me, H, then DA, then the base, then D, then C, then M, then to the dot, then to the next dot, then to the, and so on and so forth. And ultimately what that would do is give you not only the number of decimal places you have to move it, but also the fact that you got to move the decimal to the right. That's not the way we want to do things. That's a little too slow. Okay, it's good in a pinch, but it's too slow. So let me show you how I can use the table above, which is supposed to be something you've sort of committed to memory. So I'm going to write 1.0 times 10 to the negative 6 teragrams. And what I want to do is, because I'm going to inevitably be working with fractions, and because I still find even you guys, which are, the cream of a crop at TCC, really is our students that have already finished at least one semester of calculus. So I get some of the best students at TCC in my calculus-based physics classes, but I've learned that even the best students are sometimes quite rusty on fractions. So what I tell my students is to go ahead and take your quantity that you're converting and make it into a fraction. In this case, I just had 1 unit, so I'm just going to take the whole number and put it over 1. If I had something nice like 60 miles per hour, then I could choose to write 60 miles per hour over 1, but it'd probably be smarter to write 60 miles divided by 1 hour, and then I still have the fraction, but I also have the hour in a more convenient place. So that's what you're going to do, and it'll just help you because it automatically takes what's getting ready to happen and makes it deal with actual fractions instead of fractions and whole numbers, which I have found that students sometimes get confused when they try to multiply a fraction times a whole number. So the first thing I'm going to do is, of course, I'm going to use my adage that I told you about, which is multiplying by 1. So first off, I'm going to find an equivalent statement between teragrams and just grams. In other words, I'm going to go to the base unit. So what I see from looking up above is that 10 to the 9th grams is equal to 1 teragram. That's what I meant when I said the DA was 10 to the 1 and the H was 10 to the 2 and the K was 10 to the 3 and then the M was 10 to the 6, so on and so forth. So I can do that now. Now the trick is choosing one appropriately. Now that I have an equivalent statement, I can write that as 1 teragram over 10 to the 9th grams, or I can write that as 10 to the 9th grams over 1 teragram. But what we want to be able to happen is we want the unit we have to be able to be canceled out. So can anybody tell me whether the gram or the teragram should be on top of the 1?
Gram?
Yes, we want the gram to be on top. So I'm going to write 10 to the 9 grams, and I'm going to write 1 teragram there. And I'm going to mark that unit canceling out. So I've got that. Now I've converted the units from teragrams to grams. That's still not what I wanted. I actually want nanograms. So now I'm going to use yet another equivalent statement. And the equivalent statement is that 1 gram is equal to what? There's a couple different ways I could write it. I could say 1 gram is equal to 10 to the 9th nanograms, but that one doesn't look as obvious by looking at the little mnemonic tool that I used above. So I'm going to say 10 to the negative 9 grams is equal to 1 nanogram. Okay. So that's another equivalent statement. And therefore I can make another fraction. Anybody want to tell me what unit goes on the bottom this time?
The gram.
Grams.
Very good. So I'm going to write 10 to the negative 9 grams in the bottom, and I'm going to write 1 nanogram in the top. And now notice this is a neat little trick that I haven't seen any books teach people, but I like this. This is something I made up, and it helps me a lot. I do a lot of long and tedious calculations, and I've learned a lot of neat little tricks or made up a lot of neat little tricks to keep you from making mistakes and to help me find the mistake that I made when I did make one. So one of the mistakes you make sometimes is canceling out, a meter with a nanometer by accident. So I used a slash of red going from top right to bottom left. So I'm going to use a different technique. I'm going to go from top left to bottom right on the gram here. And just by doing that, I can say, oh, okay, I was canceling this one with that one. I'm never going to take points off for you not doing that. You're probably never going to find a book to tell you to do that. But I tell you, this has been wonderful for me, and it's made me a lot better at doing calculations and quickly finding mistakes. All right, so now you see all the units we had have canceled out, and all the units that we want is nanograms, and that's the only one that's left. So now the next part is sort of key. So what I tell my students to do, again, because they're often kind of weak when it comes to fractions, is I tell them to multiply all. Notice there's only 1 unit left, so I'll just stick that to the right. I could have put it on the numerator, by the way, and that would have been fine, but I could not put it in the denominator. Hopefully y'all know that, but if you don't, now you do, and you better make sure you figure out why. So what I tell them to do next is multiply all the numerators to get a new numerator. So I'm going to go 1 times 10 to the negative 6 times 10 to the 9th is a little weird to put in. And if you do it like you normally do scientific notation, you're at a high likelihood of getting it wrong. So what I would tell you to type in is 1 times 10 to the 9th, because 1 times 10 to the 9th is the same thing as 10 to the 9th. So what I'm going to type in my calculator, and I'm not even going to use a calculator on this because you can do the math in your head, but I'd type in 1.0 times 10 to the negative 6 using the exponent key on my calculator. And then I'd say times 1.0 times 10 to the 9th, and then times 1. And that gives me 1.0 times 10 to the 3rd. Now I've got to multiply all the denominators and get a new denominator. So 1 times 1 times 10 to the negative 9, I'm going to write 1 times 10 to the negative 9 here. And now what you do is you divide the numerator by the denominator. And I think you all can see that that would be 1.0 times 10 to the 12th nanograms. Okay. So that's the final answer on that one. Anybody have any questions on that?
Yeah, I was gonna ask, so because we have the same base value, can we just use exponent rules to finalize our, okay.
Yeah, absolutely. That I think it's much better for your brain to do as much math in your head as you can. And then if you don't trust yourself, at least while you're taking the training wheels off, go ahead and compute it with your calculator to make sure. But yeah, definitely do that kind of stuff. That's why I try to do it like I just did. Specifically, my grandmother had Alzheimer's, and it's one of my biggest fears is that I'll develop Alzheimer's. So there's some research to suggest that if you keep your brain active, you're less likely to succumb to that. So hopefully that'll pay dividends. All right, so everybody understands how we do that? And see how I was just able to use the fact that that order of TGMKHDA gives me all those powers. That's how I got those conversion facts or those equivalent facts. So this is the answer. Anybody have any questions on that? All right. Well, let's look at something a little more difficult. Let me see, for instance, trying to remember what ones I did with you. Got that. Yeah, okay, I did nothing there. Now let me check what I did with my other class. Yeah, that was pretty good. Okay, yeah, so I think I'm going to do for the next one, I'm going to go ahead and do my typical 60 miles per hour. So what I'm going to do now is another example, and this example is convert 60.0 mph to meters per second. Okay. First off, I want you to realize that when I write mph, that you all know that means miles per hour. But one thing I think everybody should know, and hopefully you already do, but if you don't, it's not a big deal. Miles per hour means literally you're going to take the miles and divide it by hours. So the per means divide. That's a key thing that helps you a lot of times in word problems in general. So we're going to start with that. And I'm going to do this right here, the 60 miles per hour. I'm not going to do the 60 mile per hour conversion to meters per second. That's the most straightforward. I'm going to do the one that I can use exact facts that I happen to memorize or happen to have in my head memorized already. The reason being that if I had 42 sig figs on my 60 miles per hour, then using this technique would allow me to get out 64 sig figs again, because this way is all exact. So let me show you what I mean by that. Here's our solution. So I'm going to take 60.0 and I'm going to write that as miles over 1 hour. That's what I meant earlier when I said if you have a unit that has a division in it, you can take the top and make a numerator unit and then put 1 down in the bottom for our denominator unit. So first thing I'm going to deal with is the mile at the top. And the mile at the top, I can go through things that I know. For instance, I know for a fact that 1 mile is 5,280 feet. So I want to get rid of the mile. So I'm going to write down here 1 mile, and I'm going to write up here 5,280 feet. And now I'm going to say that the mile canceled out with the mile like that. Now that gives me feet per hour, which is yay, I'm closer, but I'm not really there. So now I'm going to go from feet to inches because I happen to know a conversion between inches and centimeters. And that conversion, by the way, like this one, was exact. In other words, there's no decimal places there other than an infinite line of zeros after the decimal on 5,280. Okay. So I'm going to put another fraction bar here. And now I'm going to say that 1 foot is equal to 12 inches. And now I can see that the foot canceled out with the foot and I'm left with inches per hour. Now I'm going to go from inches, which is a British unit, to the metric system because of my conversion between centimeters and inches. And I happen to know that 1 inch is exactly 2.54. I'll express it. It's exactly by putting a 0 with a bar over it after the 4, so 2.54 centimeters. So that happens to be a reality. 1 inch is exactly 2.54 centimeters. So by doing all these exact conversions, we're going to get an exact correction to any number of sig figs. Now I can see that the inches cancels out with the inches, and I use a full X on that one. So you can see I'm continuing to use a different slash symbol each time. Now I've gotten it to centimeters per hour. All I need to do is to go from centimeters to meters, and I'll be finished with the distance part. So I happen to know, or let's ask you this. Does someone know how many centimeters are in a meter?
100.
100. And notice I took a long time in pronouncing the symbol cent. That's the reason, because obviously a dollar is made of 100 cents. So just a reminder to help you with that. So what I'm going to do now is say that 100 centimeters is equal to 1 meter. And it looks like I've exhausted all my possible ways of canceling this thing out. But lo and behold, Mr. Younger comes up with another one. Look at this. I use a curly sort of slash and a curly sort of slash like that, almost like a backwards ugly integral. Now I've gotten my units to meters per hour, so I'm really, really close. Some of you might, off the top of your head, I hope you do, know the conversion between hours and seconds, but I'm going to break it down as if we don't, okay? So first, I'm going to convert hours to minutes. Can anybody give me a fact that would help me do that?
60 minutes in an hour.
Exactly. So 60 minutes in an hour. So I'm going to write the 1 hour on top. Notice the hours in the bottom in the original number. So this is one of the weird things where I got to put the unit that I want to cancel out. I got to put it in the top now. So I'm going to say, yes, 1 hour is equal to 60 minutes, which again is another exact factor. And then I'm going to cross the hour out with a slash like the last one, but leaning the other way. Okay. So now I'm up to meters per minute. Now I need to know a fact to help me convert between minutes and seconds. Anybody want to get me on that one?
Sixty seconds in a minute.
Exactly. So 1 minute is equal to 60 seconds. And of course, if you multiplied those two, you'd get the conversion factor that I talked about, which is 3,600. So I'm going to show you yet another way to put a slash on here. Now you think I've really exhausted it, but no, look at Mr. Younger. He ends up making a X with curves. So yeah, I finally used just about everything. I've done so many of these sometimes that I get to basically like a onk laying diagonally. So it's like a loop with a circle and then with a slash and then a line across it like a cross. But anyways, that's a way to go about doing it that'll keep you from making mistakes and allow you to find your mistakes more easily. So now we see all the units that are left in the numerator is the meter, and all the units that are left in the denominator is the second. So I'm going to multiply all my numerators. So that's 60 times 5,280 times 12 times 2.54 times 1 times 1. That's 9,656,064. And of course, the unit that was left in the numerator is the meter. And now I'm going to do all the denominators. 1 times 1 times 1 times 1 times 100 times 3,600 would be 360,000 seconds. So now that I've got those, I'm just going to divide the numerator by the denominator. And lo and behold, that gives me 26.82. And the units are meters per second. And notice I put in 3 sig figs with 60. So I should be allowed to get out 3 sig figs, but if I were planning to use this number for some subsequent calculation, I'd want to keep one extra digit so I don't accidentally round off, then round off again, then round off again, and ultimately you'll get an answer that bears no resemblance to the answer that the solution has. So that's a practice that you want to get in the hang of. In all intermediate calculations, you can write an extra sig fig by putting a bar under it, and you should do that and carry it along. And then at the very end, because you've got all the bars marked, you can tell exactly where to round off the final answer using your sig fig rules. Later, we'll learn about error propagation, which will be entirely different rules. So does everybody follow that? So that tells you something. 60 miles per hour is about 26.8 meters per second. That's pretty cool. As your own example, I'd like you guys to do this in real time. It takes a couple seconds. And it's also kind of funny. I remember my first ran into this my senior year of high school when I was such a good student that I was taking Algebra 1A Part 1 my senior year, along with 3 other math classes because I'd failed math literally every year before that. So yeah, I was a deadbeat. I had no choice but to go to a community college. That was the only place that was going to accept me. But the good news is I managed to do a little catch up. So my example here is I want you to convert 1 mile per minute to miles per hour. And the reason for this is as a kid, my mother often told me, told my little brother, told my cousins, told my nephews, all sorts of stuff. Your mouth is running a mile a minute. Can you go outside and play or something like that? So yes, I would like you all to go ahead and try to convert 1 mile per minute to miles per hour. You do it, I do it. We'll see if we all get the same answer. And it should be really quick and easy. Try to do it without looking at what I'm doing. So yes, isn't that kind of ironical? At least it's funny. I mean, my mom said my mouth was running a mile a minute, and evidently she may or may not have known this, but that means 60 miles per hour. Okay, so that's just a little bit of fun. Did anybody have any problems getting that one? Okay, so there's a couple other complexities I've got to introduce you to in converting units. And I'm going to go with something that everybody in sciences and engineering should know. Specifically, everybody should know the density of water. So the density of water is 1.00 grams per cubic centimeter. I would like to convert this to kilograms per cubic meter. So the cubic meter is something I want to make sure you guys know how to deal with. And 2, I want to make sure you know how to deal with something in the denominator, which we already did when we handled the miles per hour twice. So we've gotten that part, but this meters cubed is a little different. So let me show you how this is done. So I've got 1.00. I'm going to put a gram on the top, and I'm going to put 1 cubic centimeter on the bottom. Again, I'm going to multiply by 1 such that the unit I have disappears and the unit I want in this case happens to reappear. So first off, I'm going to deal with the numerator. So I would like to change the numerator from grams to kilograms. I bet you all know the conversion fact for that one, don't you? Yeah.
1,000 over 1.
Yes, thank you very much. So yes, 1,000 grams is equal to 1 kilogram. So it might, when you're first learning this, if you're not that comfortable, what I would do is first write down 1 kilogram is equal to 1,000 grams. And then I'd look at it and see if it makes sense, because inevitably I will sometimes write down 1,000 kilograms equals 1 gram. And I know it's wrong, but somehow I write it and I look at it and I'm like, oh, yeah, that's not right. So it's sometimes very helpful to take that second to write it and then to consider the two possible options. Do I want the kilograms with the 1 on top and the 1,000 grams on the bottom, or do I want it the other way around? We've already done that here. We figured out everything. Now I've gotten rid of the gram, and we're now in units of kilograms per cubic centimeter. Now, what I want to reiterate to you is a cubic centimeter literally means a centimeter times a centimeter times a centimeter. So this is how we handle that. Hopefully you already know, but if you don't, that's perfectly normal. So what I'm going to do is, I realize y'all have already told me this too, that there's 100 centimeters in a meter. So I want to get rid of one of those centimeters, which means I need to put the centimeter on the top. So I'm going to say 100 centimeters on the top, and I'm going to say 1 meter on the bottom. But that takes care of only one of them. So I'll do another one. Now that takes care of 2 of them, which if it was centimeters squared, like an area, that would work, but I'm still not done because it's centimeters cubed. So I have to do 100 centimeters again over 1 meter. So now what you can see is that this centimeter cubed is canceling out with these 3 centimeters. Okay. Then our rule is the same as it ever was. Same as it ever was. So I'm going to multiply all the numerators. That's 1 times 1 times 100 times 100 times 100. That gives me 1 million. And the only unit left in the numerator is the kilogram. And then I do all the denominators. So I do 1 times 1,000 times 1 times 1 times 1. That gives me 1,000. And the only unit left in the denominator is meters cubed. So you can see that this basically becomes 1,000 kilograms per cubic meter. And that's the right answer. So see how we dealt with units that have exponents on them? Easy peasy, right? Okay, so we've got that. And now I want to take a little time. Perhaps some of you, or 1 or 2 of you, work in the medical field or something related to like a medical or veterinary type field. Do you know how to go from kilograms to pounds, or pounds to kilograms?
It's rusty.
Yeah, okay. So normally the idea is every kilogram weighs 2.2 pounds. That's what most people use. So what I want you to see is that using this, 1 kilogram is approximately 2.2 pounds, which you can write this way, or you can write 2.2 lbs. That works as well. I kind of like the pound symbol. It's nice and easy to work with. But using that, what I now see is that 1,000 kilograms is in fact approximately equal to 2,200 pounds. Well, this quantity right here, which is the same as this quantity, both of these guys are what we call a ton. Notice the spelling here, which equals a metric ton which equals a long ton. So those are different units that you might run into. Does anybody know how many pounds is a regular ton like we're used to? Like, you know, you say my truck out there is a 3/4 ton truck. Do you know how many pounds a 3/4 ton truck is, or do you know how many pounds there is in 3/4 of a ton?
2,000.
Yes. And yeah, my wording wasn't very good, but yes, the normal ton that we're used to here in America is 2,000 pounds. So 2,000 pounds is called a ton. It's also called, actually, let me make this a little better. I put the, whoa, all the times it switches to eraser. The one time I actually try to switch it to eraser, it won't do it. So that's called a ton. It's also called a short ton. My brother's calling. I gotta send him a message, let him know. So that's another thing to be aware of. That kind of stuff is sometimes the facts that we expect you to know. So you'll run into all sorts of physics questions where they expect you to know things like the population of the United States, or roughly you should be able to estimate the size of a dime or the size of a penny in centimeters and millimeters and that kind of thing. That all that stuff comes into play. But also, I want you to think about this. Has anybody seen people riding around town with? They'll sometimes have a truck and they'll have a trailer behind it, like a flat trailer. And on that trailer, they'll have, it looks like a big chain link fence, only the holes in the chain link are like this big, and they're made into a cube. And inside that cube is a pseudo clear plastic white container that you can fill up with liquid. Have you seen any of those boxes running around or for sale or anything? Well, those things are either a cubic yard or a cubic meter. The main thing is it's a big thing. And what you can now realize, since we've done this conversion, you can now realize that if that thing is in fact a cubic meter of water when it's full, it's going to weigh a metric ton. It's going to weigh 2,200 pounds. So I don't want to see any of my students errantly just thinking they can stick that on a trailer and tow it down the road with their Honda Prius. Or whoever makes Prius now. But anyways, that is a massive weight. So be advised, and now you know a little bit more about units. Anybody have any questions on that? So I'm going to give you an extra credit. I've already written it up and posted it in module 1. Convert the density. Oh, by the way, that symbol I use for the density, that's a Greek letter rho, spelled R-H-O. If you type into Word a lowercase r and then highlight that letter and then change the font to symbol, it'll show you what it looks like. But that's the Greek letter rho, and that's what we usually use for density. So I want you to convert the density of water to pounds per square foot and pounds, or excuse me, not per square foot. Stupid me. I don't know why I said, I think I even typed that too, like a dummy. It's pounds per cubic foot. And pounds per cubic inch. And here's a neat one. I would like you to convert it to ounces per fluid ounce. I hope y'all have noticed this before, because that was one of the things that bothered me as soon as I started learning anything about science. Remember, I told you I was sort of a deadbeat student and didn't do anything with my life till about my senior year, roughly, senior year of high school, that is. And I started noticing when I learned how to convert units that there was an ounce that would be used in one case in which an ounce there's 16 of them in a pound, and then there's an ounce again that has to do with volume. So that's the difference. The ounce on the numerator there is 1/16 of a pound, and the ounce in the denominator is a fluid ounce. So that's a volume unit and something you could look up. But that's your extra credit. Hopefully I typed it up correctly. I'm going to have to check it right after class in case I didn't. But you can look up there for it. Now, we have finished those particular examples. And it's time to move on. I can't recall anything else I wanted to do. Let me see. Anything else there? No, did all that. Okay. Yes, I remember. The other thing I want to do is there's another type of unit too, specifically for the unit of volume. There's actually a weird case too for a unit of area where you just use a number as opposed to like a meter cubed or a meter squared or a centimeter squared, that kind of thing. Does anybody know a volume unit that doesn't use like some length cubed? How about a gallon? Yep. And a liter, right? In fact, I would up the ante here. I would also say and pounds per gallon. That's what I forgot to put earlier. So that's another one you can do for your extra credit. All right, so I'm going to try to address this for you. I'm specifically talking about a liter because that's actually from the SI. So what I want to show you is whoa, there it goes again, just making my stuff disappear. 1 liter is defined to be basically the volume of a cube whose dimensions are 10 centimeters by 10 centimeters by 10 centimeters. So 10 centimeters wide, 10 centimeters thick, and 10 centimeters tall. So the volume of 1 liter is obviously equal to 10 centimeters cubed, which equals 10 cubed is 1,000, and centimeter cubed is centimeter cubed, like that. Okay. So that's a big thing to think about. And hopefully you guys have wondered in your life, what the heck does a unit of a liter have to do with the engine? So for instance, my truck outside has a 7.3 liter diesel engine. It's bought in hopes of one day being able to own and pull a camper around of any size, because the 350 with a 7.3 liters is a pretty strong engine. But a lot of people don't understand what that means. What's the 7.3 liters? And now that you know a liter is only a 10 centimeter, which is about 4 inches roughly by 4 inches by 4 inches. What volume is that on the engine? Does anybody know? Some of you might, but I'll just tell you, in your engine, and for instance, in my engine, it's a V8. So there's 8 cylinders, which are holes shaped like a cylinder. They're literally shaped exactly like, where did my cylinder go? I literally had a cylinder here just 2 minutes ago and it disappeared. Oh, I see it. I covered it up with some crap. So this is a cylinder shape. It's basically a circular end through a length. So if you imagine a hole in an engine like that, of that shape, where it's got a circular top and it has some depth, well, inside of that circular shape in an engine is a piston whose outer diameter is very close to the same as the inner diameter of that. And that piston goes all the way up, and there's a little bit of volume left up at the top, and then it goes all the way down, and then there's a buttload of volume left at the top. If you take the difference between those two volumes, that's called the displacement, specifically for that one cylinder. And each of the cylinders should be identical. So you then take the displacement for each of those, for that one of those cylinders, and multiply it by 8, and that's where you get the 7.3 liters, just so you'll know. Okay. I actually at one time used to think as a kid that it was you'd had to take the whole engine and basically put it in like a giant beaker of water and see how much water pours out, and that would be the volume. That makes some sense because it is a volume. But when I realized how small a liter was, I realized, well, crap, the engine's way bigger than that. So I hope I'm giving you a little bit more of an enlightenment by showing you that. Now, the reason I did that is I want you to know what a liter is, but I also want you to be able to convert. So let's look at yet another example. I want to take 1.00 grams per cubic centimeter, and I'd like to convert that to grams per milliliter, and I'd also like to convert it to kilograms per liter. Okay, so let's see if we can do that. 1.00 grams per cubic centimeter. Now I didn't say it, but everybody knows what number I'm dealing with here, right? What's that number? Everybody sees it's the density of water, right? By the way, Jen and Julia, I saw that you posted gram up there when we were doing, so good job. So yeah, this is just the density of water again. So what I know is that 1 liter is equal to 1,000 cubic centimeters. So I'm going to say 1,000 cubic centimeters is equal to 1 liter. And that's going to give me, in fact, 1,000 grams per liter. Okay. Now, what I need to do is do milliliters. And what I can do is say, okay, well, I know milli means 10 to the negative third. So I can say that 1 or 10 to the negative third liters is equal to 1 milliliter, like that. Right. So what that 10 to the negative third multiplied by 1,000 gives me is just 1. So I end up getting 1.00 grams per milliliter. And that's the answer. And it's also an important fact for everyday life. I like to tie physics into real life events. Some fraction of you one day, if not already, are going to have children, and you're going to have an infant at home, and your infant's going to get a cough, and your pediatrician or some doctor or patient first or somebody is going to prescribe you a medication for that baby, and they're going to write 5 cc's of medicine every 6 hours. And then you're going to take it to the pharmacist, and they're going to fill it, and the bottle's going to say 5 milliliters every 6 hours. Now you know why that's okay. We've just shown basically that 1 milliliter is the same thing as a cubic centimeter, because the density was 1 gram per cubic centimeter, but it's also 1 gram per milliliter. And the only way that's true is if a milliliter equals a cubic centimeter. So big result, 1 milliliter is equal to 1 cc. Now remember, a cc is just a easier way of writing centimeter cubed, but in case you didn't know that's what cc meant, I wanted to do that as well. Now let's do the other part. The other part said, hey, I want to convert this to kilograms per liter. So I'm going to do 1.00 grams per cubic centimeter. And I'm going to go ahead and convert the bottom to liters like I already did. So that's 1,000 cubic centimeters over 1 liter. That obviously gets rid of my cubic centimeters. And now I'm going to take and convert the grams to kilograms by realizing that, in fact, oops, wrong color. Realizing that, in fact, 1,000 kilograms is in fact equal, not 1,000 kilograms there, I did it again. 1,000 grams is equal to 1 kilogram. Okay, so you see what you're going to do is multiply by 1,000 and divide by 1,000. So I think you can already tell what the answer is going to be. It's going to be 1.00 kilograms per liter. So what we're discovering is that in a lot of different units, the density of water is 1. That's kind of nice, right? If you use specific gravity, for instance, specific gravity of water is 1, because this is the definition of what the specific gravity is. If you use grams per cubic centimeter, it's 1. If you use grams per milliliter, it's 1. If you use kilograms per liter, it's 1. Okay. And I think you might find some other interesting thing when you do the extra credit. Anybody have any questions on that? All right. So that's basically the last of converting units back and forth. Your order of magnitude calculations, I think you can get plenty of examples from the book from that and from doing the practice test, which I'll open up pretty soon anyways. What I need to go to next is dimensional analysis and dimensions. I actually would say it's unit analysis and dimension analysis. The difference being, if I'm doing unit analysis, then I'm taking all the variables that represent mass and I'm replacing it with a kilogram. And I'm taking all of the variables that represent distance and I'm replacing it with a meter. And I'm taking all the units that represent time, I'm replacing it with a second. Now, on the other case, when I'm talking about a dimensional analysis, I'm taking a variable like m, which we recognize for mass, and I'm going to use capital M for that. And I'm going to take a unit like a variable like x, which would be a length. I'm going to use capital L for that. And a unit like time, excuse me, a variable like t for time is going to be using a unit or a dimension of capital T. And it turns out that, when you have an equation, a lot of things have to be true. Well, more than you think. There's a bunch of different types of equations. For instance, we'll learn about vector equations in 2 more chapters. And when we deal with those, not only does the number have to be the same, but also the unit has to be the same, but also the direction has to be the same. In this case, we're just talking about what we call denominate numbers. Have you ever heard the word denominational? That's where that came from. So denominate numbers are numbers that have units. And if you're using denominate numbers and you have an equation, that means not only that the magnitude of the number has to be equal, but also the units of the numbers have to be equal. And believe it or not, you can use that to hypothesize formulas and then do experiments to find out the whether your answer is right or wrong. So what I'm going to do is I'll take a simple variable like x, and I'll say if I want to know the units, so let me write up here, then I'm going to replace that with a meter. And if I have a simple variable like mass, then I'm going to replace that with a kilogram. If I have a simple unit like time, or a simple variable like time, I'm going to replace that with seconds. If I have a unit like, and these, because you're in the first chapter, you don't know a lot of this stuff. So we have to give you some of it. But as the semester progresses, we're going to expect you to know more of them. So one of the things, for instance, that we might want to know is what are the units for force? Well, it turns out the unit of force is a kilogram times a meter divided by a second squared. The unit for energy is a kilogram meter squared per second squared. So you haven't covered force yet. You don't know that. You haven't covered energy yet. You don't know that. So if I ask you those questions before we get to covering forces, then I have to give you the proper unit. If I want to do the same thing in dimensional analysis, then what happens is the X becomes L, the M becomes big M, the time becomes lowercase s, the force becomes ml over t squared. Ooh, not s. Sorry about that. I was not paying attention to what I wrote. Glad I caught it now, but still, that's not good. Apologize. The dimension for energy would be meters, or excuse me, mass times length squared over t squared. Okay. I'll also give you that velocity would be meters per second, or in dimensions, velocity would be length per time, and acceleration would be meters per second squared. I'm going to tell you guys not to read it that way. That'll be more important next chapter. But I would tell you to read it as meters per second like that. But both of them are mathematically correct. And then acceleration in dimension would be L over T squared. Okay. So you might think, why is this even remotely important? Well, watch this. Let's say Einstein's famous equation. Hypothesize a function of mass and speed of light that returns energy. So we could call that function E of M and C. And we're going to do so by using dimensional analysis. Okay, so that's our problem. That's our example, if you will. So what I'm going to do is I am going to say, and this is a key part to understanding this, equations often not only have a number, but they often have several terms. Do y'all remember what terms were from basic algebra? Terms are the thing that you add together or subtract from one another. So, ax squared plus bx plus c, that's 3 terms. But the nature of it is if you're adding ax squared to bx, both ax squared and bx has to have the same units. And since you're also adding that to c, that also has to have the same units. So we don't need to concern ourselves with terms when we're trying to make a function of mass and the speed of light. All we need is to consider possibly multiplying or dividing m and c to each other at raised to various powers, and that covers all the possible cases of what a function energy would be. So if we're looking for a function called energy that depends only on mass and the speed of light, then I know it has to be of the form mass raised to some power, speed of light raised to some power. So that's the whole theory behind all of this stuff. So here's how I do it. And next I'll do it with unit analysis instead of dimensional analysis. So what I'm going to say is E of M and C is equal to M raised to the P power and c, the speed of light raised to the q power. I can use any variables I want. I've just found that p and q are usually pretty good because p and q are very rarely the actual variables that we use in physics. There are places where we use p's and q's, but right now it's not a problem. So I could use p, q, r, l, lowercase l, or script l, or something like that. You can also use Greek letters. But now what that requires is now I've got to put all these in terms of dimensions. So from that, what I know is the left-hand side has to have units or dimensions of energy. So if I look up above, I see that the dimensions for energy are m L squared over T squared. And then I got to take the dimension for mass and raise that to the P power. And I got to take the dimension for the speed of light and raise that to the Q power. And by solving this for P's and Q's, I will get a potential formula for calculating energy using mass and the speed of light. So let me do that now. I'm also going to take and reconfigure this. I'm going to say M is technically raised to the 1 power on the left-hand side. Do y'all agree with that? L is raised to the 2 power on the left-hand side. What about T? What power would that be raised to on the left-hand side?
Squared.
It'd be
Square.
-2.
There you go, squared, but in the denominator. So yes, there you go. And I think you were getting ready to figure that out as well. So yeah, that's the way I'm going to write the left-hand side. Now the right-hand side, I've already noticed that mass is m, so that's going to be capital M to the P power. And then C, we know, is the speed of light. So that just has units like velocity. So I'm going to put L over T, and that's all going to be raised to the Q power. So hopefully you're retaining your algebra skills pretty well so that you know this. Of course, the left is trivial, but the right has to become M to the P and then L to the Q and then T to the negative Q. Because L has a power of 1 automatically, and when you raise a power to a power, you multiply the powers. And T has a power of -1, so -1 times Q gives you negative Q. So now I could just look at them and compare each of the individual variables. So the variable M suggests that 1 is equal to P. And that's from M to the 1 power equals M to the P power. Okay. If I look at L, then I see that 2 is supposed to equal Q, and that comes from L to the 2 is equal to L to the Q. Now, that hasn't done all the variables, so this, I'm not done yet. I still need to make sure the other one works. So the other one is T to the -2 is equal to T to the -Q. So that would suggest -2 is equal to -Q, which says Q is equal to 2 again. And that came from T to the -2 is equal to T to the -Q. Since this implies Q equals 2, I can see now that it actually did work. See, I've now checked all the exponents on each of the variables and all of them work. So I now know the answer. So the formula is E is equal to mass raised to the P power, which is 1. So I'll just leave it as M. And then C, the speed of light, has to be raised to the 2 power. And is that equation correct? It is, isn't it? So isn't that amazing that just understanding the unit can give you such an amazing equation like that? This is not unlike the Animaniacs episode where the Animaniacs were able to figure out E equals MC squared. They did it with a little different method, but still they sort of hemmed and hawed and did some crazy stuff and came back to it. So any questions on that? All right, if I wanted to do that with unit analysis, all I would have done is kilograms meters squared per second squared is equal to kilograms to the P times meters per second to the Q. And then, of course, that would give me kilograms to the 1 power, meters to the 2 power, and seconds to the -2 power equals kilograms to the P and meters to the Q and seconds to the -Q. So I think you can see how you'd go from there. It's the exact same thing. Anybody have any questions on that one? All right. Well, technically, we've done enough. I've given you an example how to do unit analysis and dimensional analysis. I haven't done really any examples regarding order of magnitude rapid estimating. You can see those from the book. I think the rest of this chapter really is pretty trivial. Hopefully this all helps you. And between it and the numerous videos that I have on my YouTube channel, as well as numerous videos you can find at Khan Academy or just on YouTube in general, I'm certain you can find a lot of different problems to solve. You should be able to go ahead and do chapter 1 homeworks. They are due Sunday, but in light of me not covering more examples, I'm going to go ahead and move this first week. I'm going to move your homework to be due on Tuesday at 11:59 instead of Sunday at 11:59. Okay. You guys are free to go. I'm going to wait till the last person leaves in case anybody has any questions, but I do thank you all for coming. And I hope you all have a good weekend. Stay safe. And I will see you next week.
Thank you. Have a good weekend. Oh, we're not meeting on Monday, correct? For the holiday?
Monday is, what day is that?
Martin Luther King Jr. Day.
Yeah, let me check our schedule real quick. I actually have a folder already set there that should help me find that. But that is very, very much a question. So I want to double check real quick before you go. TCC.
Yeah, I know the schools are closed. I wasn't sure.
Yes, January 15th, Martin Luther King Jr. Day. It's closed.
Okay.
So, yep, we don't have that. Do any of you have me for lab? Actually, obviously you do. What I wanted to tell you is I already moved that due date for that lab to Wednesday. I'm going to post some more pictures and stuff, and I'm probably going to move that due date a little bit back further because I know there, because of me getting the allergic reaction and all that stuff, I've gotten behind and didn't manage to post the photographs or the videos you need to do that last part of the lab. So you're going to get more than wait until Wednesday to do it. Okay.
I believe I'm in Thursday evening labs. Is that
Okay,
you as
Thursday.
well?
Gotcha. That will meet.
That will be
tomorrow?
you?
The Monday lab will not meet, no classes on Monday, online or otherwise. But if you have the Tuesday, Thursday, Wednesday lab, any of those days, you do have to meet for that.
Okay.
Unless your lab instructor told you otherwise. And sometimes the lab instructor will do that.
Thank you.
You're welcome.
Have a great weekend. Thank you.
You too.
Thanks.
Thank
Have
you,
a good
Jess.
weekend.
You too. Bye-bye.